We are going to talk about the second workflow today, and Bilal is going to take us through the workflow. And as mentioned yesterday also, we are recording this session. If any of you have any objection to the recording, please let us know. Without any objection, we would believe that you are giving your consent to this recording. We are recording this so that we can share it with you, both the day's workflow recorded videos with you in a link later on after the session ends. Okay, so over to you, Bilal, now. Please take it forward.
All right. Thank you, Surajit. And once again, welcome everyone to the third day of this KNIME training using ChemAxon nodes. So I believe before we start, would like to make sure that everybody has access to this workflow. They could correctly install it or they could correctly import it. So please let us know if you have any issue with installing the license or any of the workflow, or if you face some missing modules error. So we can have a look before moving into the workshop right away.
So yes, I'm Surya here, and we are able to download that one, and it's running. And I think one or two connections are disconnected, I think. So I think we will set right now.
Okay, that's right. Uh, Okay, so please let me know where are those connections missing once we reach to that level. So I
Yeah,
assume that by
okay.
now everybody is set and they have this workflow ready. So let me
Okay.
give a little bit brief background about this workflow. There are two workflows basically within the same workflow. So I have kept this black line here. Sorry if the people have downloaded it on the first day. I did some modification, and if you have done the export or import of this workflow today morning, you will have the latest one. But the people who have done the export or import earlier, do not worry, nothing has changed considerably. Only these cosmetic changes are there. So as I mentioned, there are two workflows here demarcated by this black line. The reason of keeping those two separate because they both are taking place on different data set. So what is the data set which we're going to use today? So we have this Campbell 25 hERG bioactivity. This is a data set taking from Campbell using, so those activities are measured on Campbell target 240. These are all hERG bioactivity, and we're going to take that example and run through the workflow in a hands-on session manner. On the bottom side, you will see this is the data set which I explained in the first day of the training. So this is from a paper using MLSMR automated plant assay data. This is a quite huge data, so 300,000 molecules. This might be a little bit slower if you have a lower end computer, if your memory is not above 8 GB or around 8 GB. So I would suggest not to run entire workflow. So run it step by step. But for the practical session or for the hands-on purpose, we're gonna deal into the first part of this. But be sure that the exact thing is all being taking place in the second data set also. There is no change, only a few minor things will be related to different data sets. So the column filter will be a little bit different since the data set is different, and we have a huge data set and the assay type is different, so we are using a different type of class. So I will explain about it in the meantime. All right, so if you have successfully imported the workflow, let me show you how does it look like in your case, or it should look like. So in your KNIME Explorer, you will have this folder. It might be public in your case, but under that you will have this folder, ChemAxon's chemical data cleaning. And if you expand the folder, you will see there are two sub things within those folder. So one is data, and the another one is the chemical data ML ChemAxon. So that's the workflow we're gonna work today. If you further go ahead and expand the data, you will see there are three subdirectories of folder: configuration, input, and results. I will explain these, what are the files within those as we proceed along the workflow. All right, so let me just minimize this so that we have a bigger view here. So the workflow is basically reading these assay data set, pre-processing them, and doing some chemical sanitization. So we're gonna use mostly standardizer and structure checkers, and then we will see how we can calculate ECFP, what are the configuration option, and how to change those configuration option for ECFP. And at the end, we will have a data set which can go into a machine learning algorithm. So for the practical purpose today, we will take example of random forest model on a smaller data sets because it's easy to run in a short time. But for your information, the larger model was used to derive a deep neural network model, and I have explained or shared the detail of model architecture on the first day. Because executing only this lower part takes around 20 to 25 minutes in my computer with 16 GB RAM, and the model training takes several hours if you do not have a high enough computer given the size of the data. So we will not be doing that, but I encourage you to run through them in your free time. If you have any problem or question, you can ask, definitely reach back to us. All right, so let's start with the first Excel first node, which is Excel Reader. So if you double click on this, you will see the configuration option here. This node comes as a core part of KNIME, so it's not from the ChemAxon, but let me explain some of the option here. So this is the place you can browse your file, and this is the different option as in the second Dora mentioned that there are options to read the file from the relative path, or you can give the full absolute path also. I kept the read from to relative and to current workflow. Then in that case, I can directly go to that data file, data folder, which I just showed you in the KNIME Explorer, that within the workflow group, you have a data folder, and within that, there is subfolder called input, and within that folder, you have this Excel file containing the activity. So it makes more compact workflow and easier to follow where are the things located. But nevertheless, you can always change this option and browse your own file from some other location. In the bottom of the work, this node widget, you will see there is a preview of the file, that what it is within the file. So the first column is Campbell ID. So these are the unique for each compound. And then all the other related properties as well as the smiles string, which we are going to work today. And then P Campbell value, which is important for us to look into today's workshop. One more important option I would like to highlight here is that because I know my Excel file has the header, so if I check this option that under column name here, that table contains column name in row number 1, then it will take the first row as the column name and it will put it here as the header of all those columns. If I do not check that, then the Campbell molecule Campbell ID will be one of the row, and which gonna cause problem in the later workflow. So I believe these are the important option to know. So please feel free and click OK. Already been set, so you can execute this workflow by right clicking and execute. Some information for the people who are not much aware about the KNIME. So it may be obvious for many people, but let me just make it sure that everybody is on the same page, that each node has three lights or three colors of indication. This is a kind of traffic light scenario, that if the node is not configured and is not ready to run, there will be a red dot. And if the node is being configured, but it is not being executed yet, then there will be a yellow light. And if the node has been successfully executed, there will be a green dot, as in my case here. So please go ahead and execute this file, and this node will read the file from my local directory, and it will give me a table output. So you can see the output, and you can actually visualize the Excel file here right within the KNIME. So what are the columns? So in my file here, I have 20,000, around roughly 20,000 rows. So these are the number of compounds in my file. There are 41 columns with different types of information. So we have smiles, we have the standard type. So there are IC50 values, EC50 values, and KI. and then what kind of relationship was there. For us, the most important is this P Campbell value, because this is the more unified value reflecting or combining different type of measurement into one single value, and they are comparable to each other. So we are going to work with this P Campbell value only. So we will take these smile, the structure part, and we will take this P Campbell ID part, and we will take this row ID if in case we would like to refer back to original compound and gain more information about it.
Yeah, Bilal, I have one question here. So,
Yes, please go ahead.
this input file you have created, because sometimes what happen is when we get the data for one particular molecule, we have more than one IC50 values. So how to take account into both the values on average of it, or how do we know which one is more reliable to build a model on?
That's a very good question, and I'm going to deal with that question in the next part. So if you pay attention here, so to answer the first question, no, I have not prepared this data file by myself by hand. I just downloaded it from the Campbell directly. Target 240, and entire data set was downloaded. No hand pre-processing has been done yet. To answer the other part of the question, we will move to the next step, which is the pre-processing. So this is a meta node, and there is a small description here that what this meta node is doing. It's basically looking for missing Campbell values. So any rows or any compound which does not have a P Campbell value, we will remove it because we're not gonna deal with that. And it does the average of P Campbell value if more than one activity value is available for a single compound. And we will also rename some of the column to make the remaining workflow more abstract and more easy to use with other workflow. So let's go ahead and open this meta node. So within this meta node, you will see there are 4 nodes. One is column filter, because I would like to remove the unused column. The other columns which I just showed before, because we're not going to use it, so it's easy to remove them, and it's beneficial because it will have a less memory footprint on your system. So if we double click on it or right click and click on configure, we can see what are the columns we could remove or what are the columns we are going to include. So we are going to include this molecule Campbell ID, Smiles, standard relation and value, just for reference purpose. We're not going to use that. And these are the columns which we are not going to include further on. So please go ahead and click OK and execute this filter, and you will see all those columns has been removed. From now on, I will not go into detail of this filtering type of workflow, because I think by now it's pretty obvious that what these filters are doing. So the next one is the row filter, and I'm looking for the examples or the compound where there are no P Campbell values. So let's see what is inside it. So this row filter node allows me to look for a test column. So I said look into P Campbell value column, and I selected this option here that exclude row by attribute value. So I want to exclude the rows, and the attribute will be that only missing value match. So wherever there will be no activity value under the P Campbell column, it will remove those rows. Please execute this node, and we can compare the result of the output of this row filter node. So if you look into original data set, there were 20,763 rows. So these many molecules were there. But after filtering the MTP Campbell value, we had removed or we have achieved a considerably low amount of molecules, so only 8,424 molecules remain. So that tells us that there were a lot of missing P Campbell values in our data set. So far, is there any question here? All right. So the next part is the question, is answering to your question here, that how to deal with those multiple values. So this is the node which take care of it. The name is group by, and it allows you to set multiple ways you can group the any kind of values. So if we look into it, if we look into the configuration of this node, so the first panel in the setting is this group one. So this lets you choose the column you want to work with. So in my case, I want to have these two in my output. So the molecule Campbell ID and the smiles, because we would need this smile for fingerprint generation. We keep all this option by default, but in the manual aggregation part, you see I have brought one column which was within the available column here. So let me show you how does it work. That if my p Campbell value here is here, I will say click add, and then I will change this option to mean. I'm gonna remove it now because already I have done it, but I just brought it here to show you that how you can bring these columns and do operation on the values of this column. So what I'm going to do is that what not me, this group by node is going to do is that it's going to look into this p Campbell value, and where there are duplicates based on the ID, it will do the aggregation, and then it will calculate the mean of the p Campbell value, and you will have a unique molecules with only one single activity value. So there could be actually different ways to do this aggregate. So this is one of the easiest way to just aggregate them. There could be different approaches, but for today's purpose, let's consider that we're going to use only this average value approach.
So,
And again, yeah, please
one
go ahead.
more, one more thing you would have done it like the one more group by node you just put it and then check it out that like what is the difference? Suppose the two values are there, then what's the difference? Suppose if it is more than 5%, then you drop both the value and then go ahead with what is the procedure here. Suppose it is a less than percentage, then it makes a lot of sense. So otherwise, what will happen? Like, there is a why the labs are why the values are different. Most of the time, there is a the paper coming from the two different lab having the two different values. So if it is between 5% is allowed. Suppose if it's more than 30% is a 100-fold difference, and the best is the better you can throw it out. Suppose four values are there, only one is outlier. Even that is also can be filtered out by the outlier method. Then we can go behind this method. That would make a lot of sense. There is only one small correction we can do it here.
Yeah, that's correct. That's correct. All right, so moving forward, this next node is going to rename the columns. So I included this node here because the remaining part of the workflow, they behave as a self-sufficient entity which can take some input and put some output. So I can reuse those meta nodes as many as time I wanted. So once I do the renaming of the previous nodes, it's always consistent. Then it's very easy to reuse the same part of the workflow. If we look inside it, so what I'm doing is here is that I am converting this mean p Campbell value and renaming the molecule, renaming the column name to activity, so that the remaining of the workflow, as I mentioned, will be recognizing this activity column. And what I'm doing with the molecule Campbell ID is that I'm renaming it to ID, and it's the same reason that it's gonna be useful in the later on. So once you execute this, you will see this output here that you have roughly 6,937 compound. That's after aggregating the repeated activity value and then renaming the column of this ID and activity here. All right, so let's go back to the main workflow here. So this part of the workflow is complete. So if you little bit go down, you will see I have classified different part in order to understand it better, or in order to recall it better once you come back after some time. So this part of the workflow is kind of pre-processing of data, which will be different with different type of input file, because different type of column might be there. Let's go ahead and look into this prepared chemical data. So let's open this meta node here. So you will see there are 3 more meta nodes and 1 more nodes. So this is the advanced mole converter from ChemAxon. I'm using this of the reason is that sometimes some of the ChemAxon nodes does not identify this string of a smile. So I'm just taking that string column and converting into SMI format. It's nothing fancy, just to make sure that everything is read properly. The output will not change much, but only thing will be that you will be able to see the structure here instead of the smile string. So this is also good for visualization, that if you want to just quickly look into your data set, what kind of molecules are there, how they look like, if there are any silly mistakes and all those things. So instead of looking at the smile string, it's always a good idea to look them, how do they look chemically. So after advanced mole converter, there is another meta node, and there is a small description that what this meta node is doing. It's standardizing the molecule and checking for the structural errors. If we go inside this node, you will see, as the name mentioned, there are just two standardizer and structure checker nodes. You have seen the example of the use of these two nodes in the previous workshop, but let me again just show you that what are the options here. So these options could be changed based on the end goal. So in my case, I'm just thinking that these are the sufficient action I would like to do. So I want to remove the solvent. So how you can actually configure these things? So these are the, on the left hand side you see the standardizer options. So these are the available option here. Either you can scroll up and down and look for them, or if you have the some keyword, you can search for it. So let's say if I do the removes keyword search, so it will bring only the key node, the actions which has the remove word in their names. And adding is very simple. You probably have seen this. Just click on this and click on the add, and it will bring those actions into your standardizer action. If you want to see the more detail what these different actions are doing, so there are some help available here. If you click on here, you will see the message about it and the different options which are available. I believe for the today's session, we don't need to go into detail of these different options, but I encourage also you to look into our documentation page where these different options are described, and there are options describe what these different option means and how does they affect the molecule by itself. Another thing you could do is that if you have been already working with Standardizer, you can import the XML file. So you don't need to always do this manual selection. You can make one configuration file and then always import it based on your needs. So you can have, let's say, 2-3 different configuration options set. One is for, let's say, data cleaning, one is for machine learning task, one is for journal standardization. So different configuration can be saved. How you can save those things from the KNIME itself, you can do that. So from this standardizer node, once you bring all the required actions within your standardizer, you can click on export, and it will let you export these all options in an XML file. And that's where basically you do the import of the XML file. This is the structure column setting that I'm saying that this is a structure column. You should perform the standardization of this smile column. And as you see, you can rename it, or you can keep the default addition concatenation part here to identify what are the standardized structure. I think that are the things I wanted to talk about Standardizer. If you see the output, probably you are aware about it now. So it will give you these two extra columns. One is the standardized molecule, and this is the message. It tells you that what standardization action was performed on your input molecule. So in most cases, it's clean D, but if I see in my columns here, I would see that what are the other actions were performed. In some cases, there were some remove fragment also, and along with clean D, and probably in some cases there were remove solvent. So it means I do not have those problematic structures in my input file now. What I will do now is pass the output of this standardizer to structure checkers, and as with the standardizer, it looks quite similar. The structure checker looks quite similar. So there are the options available. You can drag and drop, you can click and add them. And for today's purpose, I'm just using these different options. So mostly aromaticity errors. So mostly checking if there are some structure problems or some valency problem. Again, same thing, you can import and export the structure checker configuration. The structure
Bilal,
checker,
uh,
yes,
sorry, there is a question. Probably you finish this meta node, then we will take that. Sorry.
okay, sure. So structure, one option I did not mention, so let me show you that option is. That is about on the second panel here, the structure checker option. So there are a few things you can change. So there are operation mode options available. So what it tells you, that what it allows you to do is that whether you want to validate the structure without fixing the detected issue. So you just want to find the problems, not fix it. Or the other option is that the structure checker will try to fix the structure for you if the fixer is available. And what kind of output you want. So you wanna merge both the fixed and unfixed structure in the single output, or you wanna separate them in a different output options here. So that's what you see here. There are two output uh, data output rows here. So one is data output 0, which tells you the fixed structure, which shows you the fixed structure, and the one is data output 0, which tells, if you have checked it, that's kept them separate, then you will see the problematic structures here. But in my case, I think I did the merge of them. All right, what was the question? I think I'm finished here with this node.
Yeah, so the question is, in column filter tab, you have not included standard type, and in removing missing P Campbell value tab, it has included IC50 and KI values in the same dataset. So is this the correct method for curating the dataset?
I mean, in this pre-process one.
Yes.
Yes.
And the column filter. No, this will.
So the question said that I have not removed what?
You in the
IC50
column
and
filter
KI,
tab.
both of them are there. Yeah, IC50 and KI, both of them are there in the column.
So if you check the output table before the column filter, you have the standard type column, which says that there are IC50, KI values, and others. And then the column filter removes the standard type column. However, the different types, the values belonging to these different types, like KI and IC50, remain there. I think this is what the question is about.
Yes, so that's where the P Campbell values are there. So as Campbell claims that they try to bring this P Campbell value in order to merge these different type of measurement into one. So there could be different ways to approach this problem. Of course, you can decide to that I'm not going to work with any other type of IC50 value other than IC50 value, or let's say the KI value. But from my understanding is that if you do not have the sufficient data, you can rely on this P Campbell value and assume that they are kind of combining all different measurement and giving you a unified measurement. That's what the P Campbell value claims to do that, and that's why I kept it here. I hope it answers the question.
Supriya, does it answer your question, or do you have any follow-up questions on that?
Hello. Hello.
Priya.
Yeah.
Hello. Yeah, thank you.
Okay, thank you.
Thank you.
And I would just comment on that question. That's a very valid and good question, and thanks for asking. All right, so moving forward, we are done with this data cleaning node. This is the node, the next meta node. As the name suggests, it will filter for these very small molecules and very large molecules. The reason is that that these very small and large molecules are by itself are not drug-like that. So in my understanding that if we remove them, they will be better for model quality. But it depends upon different type of different type of end goal. So in machine learning, in my understanding, that if you do not include these less drug likely less molecule, that's much better. So within that node, you have three individual nodes. The first one you have.
Bilal, sorry, I
Yes.
have one question. So it's on the previous node where you have done standardizer. What does this transform nitro you have put? What does it do?
Okay, we
So
can
you
look
have
into.
removed the solvent, removed the fragments, salt, clean 2D, but what does this transform nitro means?
All right, so I will tell you what it does, and sorry I missed it. So basically what it does, if you click on it, and if you click on this part here, it will show you the
Okay, got it.
graphical transformation. So sometime in your data set, you might have seen this representation, which is chemically wrong, and it just converts this representation to this correct form.
Thank you.
Since you have asked, so there are lots of actually different options available for transformation of such thing. So if you do a transfer search here, you will see it can do this transformation of aromatic oxide, diazonium, and not only that, it also allows you to bring your own transformation, which is not within this list, by using this transform action. So basically you will add this transform here, and you will define what transformation you would like to check for and do the fixing or standardization.
Sometimes we have a transition phase. Can we draw that also and bring as a custom, like transformations?
I'm not sure I understand what is transition phase.
So in a chemical reaction, we do have a formation of, for example, a 5-membered ring. When they are close by a carbonyl or an acceptor and a donor, they can make a 5-membered ring kind of structure. So can we bring those transformations?
I believe yes, if you can encode them in a smart format, or if you can draw them.
Smart,
But I
being
haven't
smart,
seen
yes.
something, so I'm not going to say exactly. But I will definitely encourage you to try it, and if you see anything which is not working, let us know. We can figure
Sure.
it out.
Okay, thanks.
Okay. So going back to the original point where I left, that we were talking about this elemental analysis, as again you have seen this yesterday. Just to quickly again recap here, so I'm going to calculate the mass and the atom count, because those are the next node utilizing these information. So I don't need to tell much about thing, but just you can see there are other options also. You can calculate all these properties. And the next two nodes are very simple row filter. So the first one will filter for molecular weight less than 150 and 700. So within that row filter, you can see that I have now set the column to test as mass, and I am saying that include the rows by attribute value, and I'm asking it to include everything within from 150 to 700 in the molecular weight. Then it should remove all those small and large molecules. And the same way you can do it for the number of atoms, that if anything is less than 10 atoms, you just remove it and exclude those things. All right, so this part is done now, and the most important part, or the one of the most important part of preparing this data set for a machine learning is ECFP. Here I would like to show you what is inside. So again, I'm using some column filter to remove some of the column generated as a result of previous one. Let's say I don't want to have the molecular mass and the other type of standardization action columns messages. So I just remove them, and I go into this ECFP and FCFP fingerprints. So let's see what is within this ECFP node and what are the different configuration options available. So this is the place you can define the XML file. You will have that file within the data directly slash configuration and ECFP underscore 6 XML. In your case, you will find there are 2-3 more files. So I'm going to explain that what those files are and how you can customize the ECFP options. So few options are right away available within this 9 node. So you can decide on the type of output, binary or bits or integer, and this is the substructure. If you select this, it will basically convert those different fragments into substructure, but it outputs them in a collection of Marvin file. So it's a little bit tricky to work with them in KNIME, especially if you do not have much memory, but nevertheless, it's just the substructure separated by a comma, so it should be very easy to separate them, so you can see what are the substructure generated as a result of this configuration. And again, this is the place, as I said, you can browse and set the configuration file option. So if you click on OK, open, browse, you will see there are 3 more files. So what I will do now, I will go to that folder and explain what is within those ECFP configuration files. So, by the way, this ECFP underscore 6 is not a convention, just for information that I like to do this naming so that it tells me that I am using the diameter of 6 in this XML file. And if you see the other files, of course, it's not correctly labeled, but here in this case, 2048 means that's the bit length. So let me open that folder and show you how these options can be changed and configured. But if you already have the configured file, you can just browse and execute this node, and it will generate the ECFP fingerprint as per defined in the configuration file. And this is how it looks like. So we have set it's a fixed bit length string, and we have set it to let me see what we have set there. Yeah, it's a bit string, so you will see 1 and zeros for all the 1024 substructure identified. So 0 tells means this fragment was not present, and if there are 1, it means that fragment was present in that particular structure here. Let's look at the configuration file to figure out the details of it. So I just open my file browser here. I'm gonna open this XML file with a text editor, and let me know if you can read the text. Otherwise, I can increase the font size. So this is a simple XML file. You will see this is the column here, parameter. So this is where you can set these 3 important options or 3 most common configuration option I talked about on the first day. So you can set the length of the parameter. So in this file, it's 1024 bit. This is the diameter, so this is 6. You can change it manually and then read in the node in order to get the different ECFP output. And the third one is count here, that whether you want to count the occurrence of each fragment or not. Since in my task, I think I'm not going to use that part, so I do not keep this as yes. There are other configuration available also. So if you look here, so these are the property values which are going to be used for ECFP generation. In a normal scenario, you do not have to worry about it. You do not have to change about it. But I will just give you a brief understanding, and it's always good to have a understanding because it helps you to decide better. So these are the properties which will be calculated for each atom, and then these property will pass through a hash function to convert into an integer identifier, and that integer identifier identifies a fragment. So if you change these settings, you will have a different fingerprints, but nevertheless, for our task or machine learning task, it doesn't affect much. By the way, how you can change those? So for example, if you see here, this is the section that these are other built-in atom property. If you wanna, let's say, use the valency of those atoms, you can just change this value to 1, and this property will be used for ECFP generation from now on after changing this value. Quickly, let's go ahead and see other files and then wait for the questions here. So as sorry, I should not open in my browser. I will open in a text editor.
So
As I
Bilal,
said,
just a quick question.
yeah, sure. Just
So
a second, let me finish this and then I will stop for a question. So as I mentioned in the previous, like length, now this is the another file. Everything is same, just I change it to 2048 and save it a different XML, so that wherever there is a need to use this length of fingerprints, I can just call this. So same way you will see I have ECFP 4096, and you can come up with different type of configuration here. Yes, please go ahead.
So in your experience, if you use this diameter of 4 to 6 for the same data set, do you see considerable differences in the fingerprint generation?
Considerable difference in terms of size, yes. Considerable difference in terms of model quality, it depends. In my case, when I improve, when I change it from the default to length 6 and diameter 6 and length 4096, my deep neural network was better performing, but it does not affect for a shallow neural network or a simple machine learning model.
Okay. And changing the diameter, does it need more computation power, or does it is not?
Yes, it would need little bit more, not considerably, but maybe few extra seconds or minutes.
Okay,
But
thanks.
that also depends upon the size of data set. If the input size of your data set is
Right.
small, these changes
Yes.
will not much.
Understood.
All right, thank you. So you see there are here two more nodes. I believe they are not much of relevance, but this is the node Marvin view. Sometime I would like to see my structures in a visual way, so you can actually execute them and see uh, those structures all in a one place. Just this is just for visualization purpose. I would say do not execute this if you have a large input data, because everything is, I think, dumped into memory. But this option is good to know always, because always intuitive to look into the data set visually. And the next one is again some removing some unused column, because just to keep the memory footprint low. All right, so that was the part, last part of ECFP. Now I will go back to main workflow. So we were within the prepare chemical data set. So I will do one thing. I think I'm gonna finish this basic feature selection and then again wait for question, and we will see how it goes. All right. So this is again just a note here that this feature selection which I'm going to do is not exhaustive. It's a very basic one. You might come up with a very advanced basic feature selection, not the basic one, where you kind of do the model training and select the feature based on that. But this one is only filtering the low variance columns, and well as looking for the linear correlation and filtering them out. So this is the node. So about this calculates the, not calculate, it basically removes the column which has very low variance. So if you look into the configuration of it, of course I do not want to do the these variance, and actually I should also remove this activity value here, because I do not want to filter them. These are not the descriptors. So what it will do, it will calculate the variance for within these each column, and this is the upper bound, that if there are not much variance within the column, then it should remove using this threshold. So if you execute this node, you will end up with less number of columns. So basically, kind of not cluttering your algorithm, the training algorithm, with unnecessary information. So it's output the table, and what I'm doing here, I'm passing this table to two different nodes. So one is the linear correlation. This node calculates the correlation between the fingerprints and a pairwise correlation, and the next node takes the input from this one as well, and based on the threshold it will remove the columns which passes certain correlation threshold. So within this column you will see I have set the correlation threshold to 0.9. So it means any columns which are correlating to any other column above this threshold, they should be removed. You can have a quick glance at what it's gonna do. So in my case, it is excluding one column. So there are at least one pair of column which has higher correlation threshold than 0.9. Again, these are very simple ways, so this is always good if you just quickly want to have a look into data set and just want to have a quick feel that how does it behave, what is the model quality. But in a real scenario, you will definitely explore more feature selection, especially if your data set is low. This option is not much relevant if you have a very large data set and if you are training a deep neural network, because as you increase the size of or the depth of neural network, these feature selection method does not affect much. If there are, if there are more features also, it's always good for a deep neural network. But as I said, it depends upon the data set you have. Do we have a question here so far on any of the things?
I don't see any questions in the chat box.
All right. Uh, so far, the workflow was.
Excuse me.
Yes, go ahead, please.
Yeah, are you trying the same data set with any deep neural network? The same data set, have you tried?
This one here, the first one.
Yeah.
No, I didn't try it. It was just 7,000 compounds or 6,000 compounds. And in my understanding, the idea of deep neural network is that if you have massive data set, that's where the real advantage is there. But I did try it with the lower data set, which has like 3 lakhs compound.
Okay. So with the same set of 1024 nodes of signature, I mean to say, you have calculated the ECPA value, right? Like the same 1024
Yes,
values. Tried that one?
yes, yes, yes.
Okay, okay, okay.
Okay, all right. So starting from the point I left, so as I mentioned, this starting part is almost same with the second data set because preparation of chemical is same, basic feature selection is same, but this assigned class column is a little bit different in these two cases. Uh, because in the second part I have the hug activity value, which is which is different than P Campbell value and which has different significance. You can say, I don't have the exact word, but you can classify them using different cutoff. So in case of P Campbell value, I took this example from a research paper. This is not a gold standard, but this is something people have been using, that at least in the HERB case, that if your P Campbell value was greater than or equal to 6.5, classify that compound as active. It means it's going to have the hug activity and it's not probably good drug molecule because it will affect the cardiac activity of the patient. So active means this, it is active against or it is activating the hug ion channel, and the rest are inactive, means they are safe for cardiac activity and you can explore them. So I just explained the naming here, that it's a bit different than the usual naming. Usually you want to have the active molecule, but in her case you don't want her active molecule to be your drug candidate. All right, let's look into assign class here. It's a very simple workflow. So I'm using this numeric row splitter node, which is working on this activity rows, and it's a double digit number, or you can say a number or integer, and it looks for this lower bound. So anything above 6.5 will be split, and you will have these two outputs. So the data accepted and data discarded will have actually filtered them out. And what I'm doing in the next one is that taking the accepted row and then adding a clause column. So I am adding extra column for all these compounds or these examples, and then I am saying that append a new column named class, and then put active as a string value in each of the column. So if we look into the output table, it will look similar to the previous one, except that you will have this class column now, and then all of them will be set to active. Now I'm using this another node here to add the same node to add the class column, but in this case I'm adding the inactive class column. So basically you can choose to have any names you would like to use, which is more intuitive for you. But in this case, I chose this active and non-active, and then this using concatenate node, I'm just combining that these two different tables into one table so that I can feed them as a training set, or for splitting them in training and test set as one data set. So you can see now I have inactive class examples also and active class examples also. So it's nothing fancy here, just very simple column assigning. And so before going to the next part, let me show you how you can do this if you have more than like one class, and how you can do the assignment of class on this data set, because this is where they differ a little bit. So if I open this part here, so there are more number of nodes. The basic idea is same, that you filter the input molecule based on a defined criteria. So the first one is that I'm splitting the input data using this criteria, that wherever the value of my activity value is greater than or equal to 20, which is in my case this column. So this is the IC50 in micromolar. No, this is not the IC50, sorry. This is the percentage of hERG activity increased at 10% micromolar concentration of the drug molecule. If you are interested, you can look into this patch clamp assay method. So basically it measures the voltage across the ion channel, that by addition of a compound, how much was the channel, how much was the voltage modulated, whether it was increased up or down, and it gives the number in terms of percentage. So I am splitting this, that wherever the voltage modulation is less than or equal to, sorry, greater than or equal to 20%, split them and then add one class, and then remaining of the data set will be now split using less than or equal to 20%, and again give them a class, so that at the end you will have a 3-class data set. You can see here that how the data set looks like, but it's not very intuitive to see all these 300,000 or 3 lakh compounds. What you could do to visualize this, that in this case I'm using a pie chart or donut chart. So if we look into the configuration, that I'm saying that generate a pie chart for me using this category column, which has 3 possible values, and aggregation method is on the number of time it has been occurred. If I execute this node and open the view, it will take few seconds, I think. Not much. So meantime, I will wait if there are any questions. Okay, so this pie chart being produced for me, and you can see now the relative distribution of those classes. So right away you can identify that it's a very imbalanced data set, and that's usually very typical for this kind of activity. I mean hERG activity. You will have lots of compound which are inactive for this molecule, this ion channel, and few of them are active for them, or the activators are there. So this tells you right away that you're gonna deal with this imbalanced class classification problem. So you should decide on the algorithm level that how you're gonna treat these imbalanced data set. So in case, let's say if we take the example of neural network or deep neural network, you have you have options to do the options of providing higher weightage to underrepresented class. So that's where the one of the advantages there. In other methods also you will find there are some ways to deal with this distribution. Let's move to the first part here because we're going to generate this machine learning model. So before feeding into this machine learning algorithm, we're going to split the data set into 80-20 ratio. So 80% of the data set will be used for training and the 20% will be used for prediction or testing the model. The same way, there is a pie chart for this particular data and its class distribution, so we can look into it. Okay, let me open the view. Yes. And again, this is an imbalanced data in this case also because that's typical for the hug activity values. This partitioning node is just one single node from KNIME core collections. So I'm saying that I'm going to do this split or relative of 80%. So 80% will be kept one side and 20% will be kept one side. And then I am saying that do the stratified sampling on the class column. So it means that the test and train will have the same relative distribution in the test across this active and non-active class, so that you make sure that there are no bias in your training or test data set. It's not so fancy stuff. These are the things usually done in a machine learning task. But our goal was here to look into deeper how these chemical cleaning tasks are performed. By no way this is a machine learning tutorial or something. These are very basic stuff here as far as the machine learning part is concerned. All right, so you have already seen the random forest model yesterday. So it's just very simple, taking one random forest learner, uh, feeding the trained data set, and then passing the model to the predictor and testing it on the test data set. I believe you have seen the configuration. There are nothing much to talk about here. We can quickly look into the scorer node, which you again have seen, but just to see what was the model quality. So you can have a here that a matrix of a confusion matrix here of how many class of active were predicted as active or inactive. You can have some error values, some Cohen-Kappas values, and some accuracy values. Basically, it lets you decide on the quality of model. There is another node from KNIME again. This is ROC curve. So you can also generate the area under the curve, or sorry, the ROC curve, receiver operating curve. So this is the place you set the class column. So in my case, this is class. And then this is the place you set what are the positive examples or what it is called. In my case, it's active. And this is the class probability which were calculated from the RF trainer node. If you execute this and open the view, you will see the ROC curve. So basically, very simple. In a very simple way, it tells you the quality of your model. So higher the curve in this direction, the more is the model quality or robustness of model. So in terms of quantitative number, this is the value. It's as close as to 1. It means you have a better classification model. All right, so the next part is remaining, which is very small one. But before that, I will stop here for question or anything else. If you had problem with the previous part, or if somebody has a good computer, they could also execute this lower part. And if they would like to talk about it, we are happy to talk about it. Okay. I think there are no questions. Suruji, should we take a break? Short one or? Okay, I think we cannot.
I think Surjit just take a break.
Okay,
Sorry,
no
sorry,
problem.
I was on mute. I was on mute, sorry. So I see there is just a question from Supriya that are these nodes freely available or are from ChemAxon? So quite a few of them are freely available and some of them are from ChemAxon. So the ones that Bilal is explicitly mentioning, like the ECFP and the property calculations and all, they are from ChemAxon. Yes, and I don't
I will
see there
show
are.
actually, yeah, Surijit, I will show what are the nodes from ChemAxon here. So if you open this node repository, if you see here within the ChemAxon, you have seen this already. But in this workflow, I am using, let's say, the small converter, advanced small converter. So this is not free. I'm using this Marvin view I showed you. That is currently free for academics, not for industry at least. I'm using this structure checker node from ChemAxon. I'm using this Standardizer node from ChemAxon. And then there is a fingerprint generation node also, which should be within, I think, screen, yes, ECFP. And also whatever is within this ChemAxon nodes, they are free, and the other sorry, they are not free. And the other nodes, for example, reading this data set, splitting this random forest, and all these things are from the KNIME analytical platform, and they are free, at least for the desktop use.
Okay. Thanks, Bilal. I don't see any other questions. So it's already 5:03. So should we take a break, or should we just, how much time do you think it will take for us to wrap it up? Another
I
20 or 25
think,
minutes?
yeah, less than that, to 10 to 15 minutes only, not much.
I guess then let us do that, and we will take questions again, and then we will wrap it up. If it is 10 minutes, then it does not make sense to take a break now.
Okay, okay, that's great. So then see you in 5 minutes.
Uh, Bilal, I said I think that we should not take a break now, because if
Okay,
it is just 15 minutes, we can
okay,
continue and finish it off.
okay, that's good. So that's good. The rest of the thing which I wanted to talk about is that what I'm going to do this with data set. So as I said, it's take a long of time to execute, like say in my computer 20 minutes. So I did not want to show it live, but you can execute them obviously, and you can also find the output of these exercise for this big data set. Within the data folder, you will have the result. So this is the output for those big data set, and all the values has been calculated, of course ECFP, after passing it through Standardizer and structure checker. So in practice, you can take this CSV file and feed into any of the machine learning algorithm you would like to use. In my case, I used this to generate a deep neural network using Python, which probably is out of the scope of today's workshop because it's about KNIME only. Of course, you can do this exercise in KNIME also. It's just my personal preference that I was more comfortable in Python for this task. But it should not stop you from trying. So if you see here the nodes type, you will find there are free nodes again from KNIME core distribution. You will find these machine learning nodes here, different type of so neural network, and you can also install Keras or the TensorFlow extension nodes within the KNIME. You can try all these things within one single platform. As I mentioned, so this was just my personal preferences that I wanted to do that in Python. So in case that's also the case with you, this file is available. So basically, I am just again filtering those unnecessary columns and writing the output of this one in a CSV file. You can write them in an Excel file or any of the supported format. So it just tells me, or it just allows me to browse the file where I want to write the results, and then just execute it, and you will have the file. The another thing which I wanted to at least talk about is that so we use ECFP, but that's not the only thing you can do in terms of generating descriptor. So I will just quickly show you the property calculator you might have seen already. So using these nodes, you can calculate some physicochemical properties. They're especially useful if you have a small data set, or the case is that you want to have a chemically intuitive understanding that what are the features important and how it can help you to rationalize the designing of the molecule. So it should be fairly easy to combine these things in a
And
node.
Bilal,
Yeah.
in that folder only, in that node only, that meta node one standardizer is missing. You could have put standardizer it calculate, because The second one, hydrogen bond donor, is not calculating
Okay,
because
yeah, yeah, actually, that's correct, that's correct. I should have actually passed this data.
yeah.
So I should have passed not that connection, but this connection. So
Okay,
that's,
okay.
thank you, yeah.
Yeah.
The same way, actually, you can combine also. So there are, you will see many papers or many researchers, they sometimes combine these different descriptors. Let's say combining ECFP with this FISCAM. So it's a quite iterative process. And in my case also, actually, I'm just showing you the final iteration. That's how I arrived into ECFP and this kind of configuration of ECFP. But nevertheless, I tried different options. I tried some other descriptors, let's say from open source also, from ChemAxon, some. So it's a quite big area to explore, but these are the one usually it works for in most of the cases. The other thing is that I want to show you, or at least I talked about on the first day, is how to analyze those misclassified examples. So if I go into this meta node here, libmsc classified, you will see there are a few nodes here. So this is a CSV reader. So what I did that I identified those misclassified molecules within my machine learning exercise in Python, and I saved them in an Excel file, in a CSV file. So I'm reading those molecules which were misclassified. It means they were classified wrongly against their original activity class. So I just read those file and it's a smaller one. You will have only 11,054. I'm just reading their PubChem ID because I can get the molecules from my original data set. So this is the next node. What it does, it's a reference row filter. So it filters the incoming, I should put it here, it's much easier to see. Yeah. So what it does, it filters this incoming data based on these reference rows. So it will look for these Campbell ID and it will give me the remaining data as an output node, and provided if I execute it. So it takes not much time, and you have the filter data here, only those 11,054 compounds, and now have their smiles and the activity value. So my goal was here to do this library MCS. You have seen the usage in the second day workshop also. So my goal was to just, I was wondering why are those examples misclassified? Are there any chemical features which are common among them? So you have seen the details of it, the background of it. It basically calculates the maximum common substructure for this given 11,000 compound, and then you can see what was the most common scaffold to let you decide on the next course of action. Hopefully it should execute soon, but yes. So of course, it does not give you right away the graphical interface. So, but with a slightly more few nodes, you can actually you have seen this workflow. Basically, you can bring that workflow from the yesterdays and get a graphical visualization of the most common type of fragment within your misclassified examples. That was all about it. I think we can talk about if there are anything missing or if you have any questions or problems.
Yes, so I do not see any questions further. So as I
Bilal,
said, you like
Surajit, yeah, go
sorry,
ahead,
Dr.
please.
Surya.
Bilal,
Sorry.
see that the tautomer node, like there is a node which is yesterday I explained about the tautomers.
Yeah.
So the tautomer node, what happened, like it is giving tautomers one by one. Suppose for a given compound, like what are the possible tautomers if you want to have it in the same row, if you want to do that one.
I think what I understood from the question that you're asking what that tautomer node does.
No, yes, that is giving us a lot of tautomers. Just pull out, yeah, just take it out,
Yeah.
take it,
Yeah.
and just connect to any of the standard nodes. Connect to the any standard structure nodes. And suppose if you create a tautomer, if you see that there's a fourth option, that's an all tautomers, right? You see the fourth option.
Yeah.
If you click the fourth, that option, then it is able to pull out all the tautomers. But what is happening is it pull out the tautomer one by one. For a given compound, the tautomers are coming in a single line.
You mean in the same row?
Yeah, the same in a single column. It's not the same row actually. I need it in the same row. Yeah.
Okay, I think let's look into it probably. So let's execute this and see. I hope it does not take much time. Okay, it will take maybe less than a minute or something. Meantime, it's executing. I think Surjit, yesterday you asked how to create a meta node. I can quickly show that. So basically, meta node is a way to organize your workflow. If I do not bundle them, this is gonna be very messy. And that's what my original workflow was, very messy, which I only could understand. So in order to create a meta node, it's very simple. As for example, let's say I have these two nodes here, which does some function, and I wanna do them, combine them in a meta node. So you select them, and so once those nodes are selected, you click on them, right click, and then say create meta node. Of course, it will unexecute them if your nodes have been executed. But if you click OK, it will allow you to give it a name, and then let's say in my case it was pre-processing. For many people, it might be very trivial, but let's assume that somebody might need this. So all those nodes are now combined into a compact one. So this is a way to clean your workflow. All right, so our totem has been generated. Let's see what you were talking about. So, okay, it gave me the distribution.
Yeah, it's giving a single line. You see here.
So all tautomer and maximum number of structure. Okay.
Because why I'm asking this question is, suppose if I have this option, but I can use this all the tautomers for the data augmentation in deep neural network. So when you are going for any of the squeeze net or something like that, like for suppose if you have very less compound, and you go ahead with the tautomer and try to understand that, like what could be the small latent spaces coming. So for that purpose, so you can have the multiple tautomer, multiple conformer, which will give the better result actually.
Dora, do you know anything about this?
So
No, it's not giving. Now I have tried about that one. It's not giving actually. This is coming in the.
Would it be possible for you to maybe write in an email and send some screenshot? Because I understood something.
So the goal would
No,
be to have, sorry, go ahead.
you are breaking.
Go ahead.
No, actually it's breaking. Actually, like there is one more way is that like you can do the unpivoting. You can do that one. If you do the unpivoting, it is possible to bring it actually. But the point is, if you have more number of data, like the amount is very high, means is very difficult. So if there is one more option to make it the parallel one, that will be very helpful. Number one.
Okay.
And all these ChemAxon nodes are will support the Spark. Spark support will be there.
Sorry, which one? Spark.
Yeah. Suppose the data is too huge. I can run through.
Parallelize the execution. I think not. We will have to double check, but my latest information is that.
So your question was about this distributed computing, right?
Yes. Yeah.
I think, as Dora said, no. But
Okay.
Parallelize them.
But I don't know how Sparks work in KNIME. Does it allows you to?
Yeah. It works. It worked
No,
very
I mean
nice.
it works in KNIME, but what I was asking is that, so let's say you have a huge data set, so does it allow you to execute same thing in parallelly? So in theory, if that's the case, these nodes could be working with them. I don't know.
No, I never tried that one, but the
Okay,
point is
you
whether
tried
you
it.
yeah, if you have a case study, I think we will check it out. How is it working?
Okay, that's great. Actually, I'm at least interested in understanding this thing and probably passing it to the production team if they will come up with a solution for this. It's gonna
And
be a nice feature, definitely, because these days more and more things are moving in big data and AI, and that's where you can leverage the distributed computing much easier.
and one more, I may need one more example. You use the DL4J node. There is one more group of node called DL4J node. You might be hear about that. So you do the deep learning through that one. So it will support the GPU in the KNIME itself.
What is the name?
DL4J.
Probably I do not have installed DL4J.
Yeah. So if you have a DL4J, it will support the GPU.
Okay, that's great. That's
So
useful
you
for
can
me.
so if
Great.
let me to share the screen. I can share it
Yeah,
and then
yeah, okay.
Okay, I'll just
next first one.
yes.
So you can see here like all kind of stuff is there.
That's great, actually.
The one good thing about this one, it will support the GPU.
Yeah, then it will be quite easy to even deal with this large data set in local computer.
Yep.
That's great. Thank you. Thank you so much.
Okay, so I do not think there are any other questions. So just some housekeeping information again. We will send you the recorded sessions of these 2 days, yesterday's and today's. The license that you have for the tools is till 23rd of October, and it includes majorly the workflow or the nodes that were required for these two workflows that we showed you. However, as Bilal showed, there are quite a lot of other work nodes also that are there within the ChemAxon node repository. If you want to use any of them, you can let us know. We can issue you an additional license for them so that you can build your own workflows. And if you are trying to build your own workflows and you need certain help, some help from us to build out regarding certain ChemAxon nodes or KNIME in general, you can write to us. We can help you out with that so that you can try to understand how you can utilize KNIME and the KNIME nodes along with the ChemAxon nodes to your best possible benefit. Okay, so I think that is majorly all. Thank you all for joining in for these 3 days. Thank you for sparing 1.5 hours each day, and I'm just happy that we were able to maintain the time on all the 3 days. And a big thanks to Dora and Bilal for taking us through this, and thanks to you all for your active participation. So if we do not have any questions or comments on this, we will conclude the session now.
All right. Thank you, everyone. And I would just like to add this last. In principle, we were taking this workshop to give information or pass the knowledge, but nevertheless, I also learned few things from this one. And thanks for those who have commented such useful insights.
Thank you, Suraj and Bilal and Dora for your time. And behalf of the attendees, thank you everyone for having a very nice 3 days, 1.5 hour session each day. Thank you very
Yeah.
much.
Thank you.
Thank you for your active participation. Bye bye.
Bye.
Thank you.
Bye.
Bye bye.
Bye.
Bye.